Hi, in this chapter we're going to talk about how to map GIS data. Typically, when we do any sort of GIS project or analysis, the end product of our analysis is going to be a map, some sort of visual cartographic product that you can give to someone. And if this map looks like junk, even though your analysis is great, people are going to think your analysis is going to be subpar. So here we're going to talk about some of the techniques by which we make maps and represent and render some of the data that we have in the GIS environment here. Typically, this is what we call a general reference map. This is a map that I made when I worked for the military. It shows a lot of different features here. It's got roads, it's got green stuff here. Obviously, this green stuff is going to be vegetation. It's got these blue lines and these blue polygons, and you would imagine those are going to be for lakes and rivers or other types of waterways. So we have general reference maps here. And we have geographic data components. We have layers or themes or feature classes. So these are our crimes. These are our states. These are our rivers, roads. These are our different things that are going to be layered on top of each other so that compose the map eventually. We have individual. So within each of these layers or themes or feature classes, we have individual instances of a single crime or a single river or a single road within those, which is called a record. And then we typically use attributes to describe them. So a river, well, what are some things we want to know about a river? Well, what's the name of it? How long is it? Where does it start? Where does it end? For a crime, what do we want to know about a crime? We don't want to know the name and where it ends. We need a different set of attributes to describe it. So we would need, the type of crime, the address, what time of day, what day of week, what type of crime was it? Part 1, Part 2. Maybe information about the victim or the perpetrator. Okay, so some of that. Okay, and typically when we show this GIS data, well, we need some things to make sure it lines up all the math stuff that I kind of talked about a little bit before in Chapter 1 going on in the background. Okay, it's got to have a defined datum, coordinate system, scale, projection. And we talked about identification. Okay, this is pop-up features for a specific feature. Okay, this is what we call the identify button. Okay, when I click on identify, it's going to give me the attribute information for this. Okay, and this information here is what we stored in this GIS database. There's obviously a lot more information about France, but this database that we're working with here just stores this information. And then I can click on this here, and this is what it looks like in the table. When we map GIS data, we can map any one of these columns. So you see these columns here, the square miles, or the population, or the currency type, or any of these. We can map any of those attributes and symbolize it appropriately. So you can see here for North Carolina, this is a map of population. Okay, and you can see population for the year 2000, how I've grouped it. You can see it's high in Wake County, Mecklenburg County, Cumberland County. We're over here in Durham, here at Guilford, and Forsyth County. Yeah, this is a pretty complex map here. This is female age-graded cancer mortality rate standardized per 100,000 population. And this is for females. We might talk about this map in public health and what all this female age-graded rate means. Okay, what does all this really mean? But this is what we call a quantile map, where there's about 3,000 counties in the U.S. The lowest 3,000 are green. The next are light green, the next are yellow, the next are orange, the next are red. Okay, this is for females. Now, this is what it looks like for males. Okay, slightly different patterns. And you notice the national median for men is a lot higher. Okay, the high is higher. Okay, but look at these different patterns. So men, the higher rates for men are all in the eastern part of the U.S. For women, it's kind of concentrated in the west and the kind of upper Great Lakes and the New England states. So sometimes we can map two different attributes at the same time so we can look at correlations or relationships between them. Okay, values have a quantitative relationship, and this is one that we talked about before. We looked at the age of houses versus the number of cases of lead poisoning. And you can see here, the larger the dot, the darker. Okay, you can see these dots here are really small, and they're in lighter areas where they weren't using lead-based paint. Okay, so we can start to look at these relationships, okay, where we show multiple variables on top of each other. And it gets pretty ugly pretty quickly on a particular map. Typically, we work with different types of data fields. We will work with character strings, okay? Nominal data, Durham, North Carolina, integers that don't have decimal points, floating points, which have decimal points, and dates, okay? So like October 1st, 2001. How can we view it? Okay, we have data, different types of data. I know you're covering this in your quantitative analysis courses. I know we'll do that in our courses too. We have nominal data, which is like a town name or city or state. It has no mathematical property, so I can't compare it. I can't say North Carolina is greater than Wyoming or is greater than Georgia. Now, there's things about them, like its population, or its population density, or its median age that we can compare, but not the actual name itself. We have categorical data, so we can look at a crime type, a land cover classification, or a population class. We have ordinal data, which ranks data from 1 to 50 for highest to lowest. We have interval and ratio data. These are kind of our numerical data. When we look at numerical data, interval data versus ratio data, one is based on a true zero, one isn't. So with ratio data, if we have a population of 1,000, I can say, well, the one with a population of 2,000 is twice that. When we look at degrees Fahrenheit, if it's 50 degrees out, I can't say it's twice as warm out if it's 100 degrees, because we can go below 0 for degrees Fahrenheit. Okay, in ratio data, we can look at degrees Kelvin. Also, we can look at interpreted data. Okay, this gets a little bit complex here, but we can assign scores and grade them or whatever based on nominal classifications and assign them kind of suitability scores. So we can kind of turn that nominal data into ratio data to be compared with things like utility cost or population. Census data. This is what census data actually looks like. Census data has a variety of different types, but the numbers don't necessarily mean they are interval or ratio. You notice here, this is called the FIPS, Federal Information Processing Standard. So you can see for North Carolina, that's 37. For Alabama, it's 01. And it goes from 1 up to 55, and it's always saved to 2 places. For Durham County, it's 063. And when we concatenate them or put them together, it's 37063. So for Durham County, the FIPS code is a unique way to identify every county in the United States, okay, and sub-county units when we get into census tracts and census block groups. So there's 31 Washington counties throughout the United States, but there's only going to be one Washington county in North Carolina that starts with 37. Okay, the one in Vermont will start with 51. Okay, the one in Rhode Island will start with 42 or whatever they are. Okay, and you'll also notice here for the FIPS, it's lined up to the left. If you look at the column here, it's lined up. I think I got it here. It's lined up to the left. You notice when we look at population, which are numbers, they're lined up to the right. So they're what we call right justified. When we look at text, it's left justified. So be careful for those. And those are some tricks so you can see what type of data we're working with. Because if I add up county FIPS plus something, it's going to treat it as a text, and it gets ugly quickly. These are some of the rank comparisons that we can do to things. Now, with ratio data, we can multiply and divide, which we can't really do with interval data, which goes below 0. We can reclassify data. Raster data can also be represented by numerical or categorical data, say elevation. Like vector data, be sure you know how it's classified. We have things called color ramps, which go from, say, light yellow to brown or light blue to dark blue. And when we have these color ramps, we imply some sort of quantitative relationship between them, meaning, all right, these are somehow related. Now, if you look at a map of the United States, you don't go from yellow to brown to dark brown. You have different colors. You got a red, a pink, an orange, a blue. So we just try to show the differences between those. Now you can see elevation data. We go from black all the way up to white. Okay. And then this is national land cover data set, so you can see green. What do you think the green represents? Probably vegetation. The red and the pink is going to represent urban areas or high-intensity urban areas or high-intensity residential areas. Okay, so you don't see any color gradation there. The pink to the red means something with urban, but it's going to be totally different than the yellow. And then we also see here these rivers right here. This is Pittsburgh. Okay, also the same thing here. I've kind of zoomed in for a later up here in Pohick Creek. So you can see the blue is water. Okay, and then I have some other things here, some high intensity residential here at the pixel level. And you can see the little squares that compose it. Now here's another one here for Durham, Burlington over here, Mebane and Hillsborough. Okay, you can see another one here. This is the red is the urban areas, and then we have our other areas here. Okay, we have a digital raster graphic too. Okay, this is just a type of map based off a standard color palette. So typically, you notice the Salem Lake here is blue. Why do you think it's blue? Because water's blue. Okay, and that's how we represent water. And so these are some maps. And then typically we can classify them. Typically point data is represented as points or graduated symbols. Polygons get colored in. This is what we call choropleth map. But keep in mind, you might see this on a quiz. The same data can be shown a number of different ways. Here's population that I had before. And this is for the entire county. Okay, this is for the entire county. So you can see Wake County and Mecklenburg County have high populations. There's only 2 of them in this darkest class here. And we know that the population is either 421,000 up to 695,000. Do we know what it is exactly? I don't know, probably not. We just know it's in this range. So when we do make maps, it squishes the data or it kind of groups the data. I don't know the exact population of these 2 counties here, but I know it's somewhere here. One of these 2 here. Okay, and even if I were to cover up this legend here, I would still get an idea of what's going on with the map. I could see what are the high counties, what are the low counties, even though I didn't have use of this legend. So using a color ramp is useful in that regards. If I had these as purple, yellow, green, different counties, you need the legend and have to rely on the legend to do that. This is point data here. This is point data. And you can see we have point symbol maps here. So the larger, the more, the lighter, the low, okay, or the smaller, the small. So the small dot means the less of something. And this is PM data. This is particulate matter data. Okay, so you can see the smaller the dot, we have less particulate matter. The larger the dot, the more. And then you can see I have average family size. We have something called an equal interval map versus natural breaks versus quantile. So how we actually display the map is that we have our average family size. You can see this is point. You can see the difference between 2.75 and 2.86 is about the same as this to this to this. This has a difference of about 0.1 to 0.12 to 0.11 for the average family size here. You notice there's a lot of them in this class here. Okay, so the regional variation is a little different. This is called natural breaks, in which we let the computer pick out what we want. And we have something called quantile, where we just say, let's line them up from 0 to 100. Okay, the first 20 go in this class. The second 20 go in the next one, the third 20. So you notice here the difference between 2.25 and 2.36 is 0.11, but then 2.59 to 2.86, that has a much higher range. Okay, 2.47 to 2.51 is a lot less. Okay, and then we can look at standard deviations, how far they are away from the mean. So there's different ways. This is the same exact data. Average family size represented a number of different ways. And now we can view a histogram of this here. Okay, and you can kind of see the histogram, how it kind of goes up and down a little bit here. Okay, this is what we call our normal distribution. It's kind of high in the middle, like you saw before. The ranges for those middle values were a lot smaller in our quantile. Okay. And then with our quantile, you can see in our ArcGIS software where our divisions are in these blue lines. And that's about it for representing maps.